Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Dr. Halim Abdul Latiff. My name is AINUL AFIFI ZAFIRAH binti Mazlan, ID 25541. This will be my extended assignment presentation for the question 1C, Deepwater Hydrocarbon Exploration Improved Shallow Section Imaging. Today I will be presenting 4 sections of my presentation, which is firstly, determination of incoherency, secondly, seismic technology to improve incoherency, thirdly, advancements in the knowledge for the seismic technology, and lastly, the conclusions. So first of all, this is the exploration area of offshore Sabah, and the area that we're looking at is deep water, which is starting from outside the outboard, which is this ND area, and I believe the section that we are looking at is around this section, and the section that was given to us is this. So the determination of incoherency in this area, first of all, let's look at the bottom segment, which is the basement, and this is predicted to be the pre-carbonate section because the carbonate section starts from this one. And also what we can see here is that the bottom layer from 6 to a time to around 5.2 to a time is very chaotic, and this is because of the complex geology. Geologically, Sabah basins are very influenced by the tectonic activities, for example, the subduction and collision that happened during the Miocene times. And here we can see the weak amplitudes and frequency. Same goes to this section over here. And here, starting with the carbonate section, we can see that the amplitudes are also going very chaotic. However, it's quite different from the ones below, as it is the pre-carbonate section. So the effects here are due to the carbonate itself. Here we can see some discontinuities, and from 4.5 seconds to a time all the way upwards to the shallow section, we can see incoherent and poor fault imaging, as well as some probably shallow gas absorption effects over here. So basically what we're trying to do is we're trying to improve the imaging for the shallow section, which is the main focus of this question. So we want to improve the fault imaging, and also we want to remove the noise and other related effects at the shallower section. Moving on to the interpretation for this section, we can see, as I've explained earlier, the different units are divided based on their amplitudes, and also their seismic phases. So first of all, we would like to see how we can improve the data, the existing data, before we go on to the imaging itself. So we want to improve the data preconditioning. First of all, we need to enhance the signal to noise ratio, and then we need to also have the direct arrival attenuation, field and residual statics, and also random noise attenuation. Also, we need to have the near offset gap filled with traces according to the nominal geometry. We need to fill in the traces in the cable length. We also need 3D seismic vintage, and for shallow section, it would be recommended to use pre-stack depth migration as well. And also, we need to use angle stacks, processing reports, acquisition report, stacking velocity, and also coordinate for seg-y. The first technology I'd like to propose is the ocean bottom node. The value of the new OBN survey is expected to address subsurface uncertainties due to poor quality seismic data associated with shallow gas and maximizing exploration evaluation, focusing on the shallow water near field exploration potential. And the reason why I'd like to propose this is because on the seafloor, we can actually minimize multiples and ghosts, therefore resulting in a much better data for imaging and processing later on. The second technology I'd like to propose is the full waveform inversion. So for the full waveform inversion, we have a starting frequency of 3 Hz. The phase values of the first arrivals are used, and the test runs using a subset of the dataset. And then we have the starting model, which is the travel time tomography of the first arrivals. The ability to predict the data is tested, and also the wavelet is developed using the direct water arrivals by designing a Wiener filter. And lastly, wide-angle refraction data recorded by hydrophones used after filtering frequencies. And for these, the frequencies recommended are around range from 2 to 7 Hz. Now this is the inversion strategy and also the parameters recommended for improving the incoherency for inversion. For acoustic full waveform inversion, we have frequencies ranging from 3 to about 5.2 Hz. The model size would be approximately 78.5 by 22 by 12. Depends on the size of the basin that we're looking at. And also the grid spacing would be 50 meters. smoothing would be applied to suppress artifacts, and the iterations would be 30 iterations at each frequency. Moving on, this is the summary of the full waveform inversion methodology. First, we have the source wavelet, we have the starting velocity model, and these are the acquisition geometries. Once we forward propagate, we can get the modeled shot, and we can examine the differences with the seismic before we get the residual, and then after that we have to backward propagate in order for us to get the velocity gradient, and this will be added with the updated velocity model. And then again, we have the continuous iterations going on and on, as I've explained just now. So the next technology I'd like to propose is broadband decoasting, especially for a shallow section where there's a high tendency to have a lot of ghosts in the shallow region. So the objective of decoasting, first of all, is to recover the low frequencies for improved seismic inversion, also to correct velocity and inversion, also for recovery of signal within the seismic bandwidth for improved resolution, constrained optimization solution for ghost parameters, improve the spatial and azimuthal resolution of subsurface parameters, and lastly, extend temporal and spatial resolution of the seismic method. So as you can see, this here represents one ghost, and we want to eliminate those ghosts by using this technology called broadband deghosting. And there's also technology, for example, 3D broadband deghosting that is being used in Sabah as well. Next, I'd like to propose demultiple methods, and this is also relevant for a shallow water section because the shallower your section is, the more multiples you'll get as compared to deeper sections. So, multiple removal based on prediction and subtraction can be divided into 4. Firstly, there's predictive deconvolution, which predicts multiples by a simple time shift per trace and adaptively subtracts from input. This assumes vertical propagation in water layer. And then we have Taupi deconvolution, where the prediction is done per angle in linear radon Taupi domain, which is much more reliable. However, this assumes constant water depth. Then we have an advanced model-based prediction of multiples, where it takes into consideration the variation of the water depth, and it also is a wave field extrapolation through water layer to predict multiples from primaries. And finally, we have the SRME, which is a data-driven convolution process to predict multiples directly from the data. This automative technique predicts all different types of surface multiples without the model. So this is more of an automation technique, which is the newest and the most updated technology. We also have radon demultiple, one of the processes which I've explained earlier. The objective of this process, high radon demultiple, is to attenuate multiples that can be discriminated from primaries while preserving the primary signal. And this is especially important because we need to preserve the amplitudes of our section, and the parameters are minimum and maximum move out, zero offset time. Domain is enthalpy domain. And this is an illustration of how the multiples look like. As you can see here in the shallower section, there are more multiples, so we'd like to remove those multiples in the shallower section and obtain a better output. The next technology I'd like to propose is also the least square migration. So in least square migration, we have divided into least square Kirchhoff and also least square reverse time migration. Basically, both of these models come from the same equation, D equals to LM, where D is the acquired data, L is the modeling operator, and M is the model. So with least square migration, basically, you are able to eliminate the unwanted noises, especially at the shallow sections, and improve the strength of the amplitudes. For example, if you use LSM on shallow section in Deepwater Sabah, you're actually able to improve the strength of the amplitudes and frequencies, and also at the same time remove the background noise, the ones that are not necessary for our data. And this is also Born or Kirchhoff linear modeling operator that can predict seismic data D from a reflectivity function M. And here, LSM inverts L by minimizing the energy of the prediction error. This is some more explanation on LSM, where it is taken from the concept of forward modeling. And then the basic concept is the reverse time migration. And when we apply least square migration, you're actually inverting the original formula here. So it is basically an inversion. Here it's an inversion-based algorithm. The model data are fit to the observations. And RTMs based on a fixed background velocity model linear inversion. And forward modeling is based on reflectivity demigration. Moving on, this is the last technology that I'd like to propose, the compressive seismic imaging technique. So here are a few parameters that can be used in this technique. First of all, the receiver's layout would be 300 by 300 meters hexagonal and 150 by 150 meters hexagonal. The total number of receivers deployed is around 1457. Source layout is 50 meters, plus minus 35%. Total number of sources would be about 108,000 sources. So the more sources and receivers, naturally, the more accurate data we will be able to achieve. Line kilometer of sources will be about 2015. Natural bin size would be 12.5 by 12.5. This is much more preferred compared to a bigger size, because when you have smaller bins, you will be able to get higher resolution. Max fold for natural bin size, 1612, and max fold for 25 by 25 bin size is 5,983. Again, these parameters depend on the data that we're looking at, and these parameters are deemed suitable for Deepwater Sabah, as Deepwater Sabah spans over a huge area of interest. And here are some advancements of knowledge that can be integrated into deepwater hydrocarbon exploration, especially for Sabah Basin. And this is also based on a paper by Petronas, a study by Sandeep Kumar et al. 2020. They've proposed to use dual and multi-measurement streamers, 2 and 4 component seabed seismic technologies, multi-azimuth and full azimuth seismic, deblending, triple and penta source blended acquisition, full waveform inversion, as I've explained earlier, reverse time migration, and finally PS converted wave imaging. And here are some additional advancements in seismic acquisition, processing, and imaging, also done by the study by Petronas. So there are 4 main advancements, which are seismic survey design, marine streamer seismic, some processing steps, and also some challenges that can be overcome currently and also in the future. So first of all, for the seismic survey design, is based on, there are a few methods, for example, surface-based designs, 3D ray tracing, pseudo-analytical and finite difference modeling, acoustic and elastic domains. For marine streamer seismic, it is a combination of novel streamer towing configurations and advanced deghosting techniques. For processing steps, we have deghosting, demultiple, full waveform inversion, Q migration, and reverse time migration. Q migration and reverse time migration are both some advanced imaging techniques, processing techniques as well. And the challenges that we'd like to overcome, especially for this case, is for shallow water multiples or reverberations, shallow gas absorption effects, interbed multiples, thin reservoirs, and also complex geology. And these are most relevant to Sabah Basin, as Sabah is very well known for its complex geology. It's very different compared to Malay Basin, where the strata is mostly horizontal. In Deepwater Sabah Basin, you have very complex geology at the basins, at the basements as well. And for this specific technology, we can actually overcome shallow water multiples at the same time as well. So to conclude my presentation for today, I'd like to start off by saying that the application of integrated seismic modeling, innovative data acquisition, and imaging technologies has indeed played an important role in unlocking the subsurface complexities in offshore Sabah Basin. And also the integrated analysis of seismic signals can contribute to the processing and imaging, and consequently it greatly helps with the seismostratigraphic interpretation, especially in shallow water environments. And based on my presentation, I've already proposed some new and old seismic technology, including OBN, ocean bottom node, full waveform inversion, broadband deghosting, demultiple, least square migrations, and also CSI. Finally, I'd like to recommend for an in-depth study and R&D on advanced processing and imaging techniques, especially in Deepwater Basin Sabah, due to its complex geology. And as we know, complex geology requires more finances and more time for research, so there are still many features undiscovered Hopefully, we'll be able to discover more information as technology evolves and as we explore more beyond the current deep water basins that we already have. So these are the main references that I've used, which you may also refer to. Finally, this concludes my presentation for today. Thank you so much, Dr. Halim, for evaluating my extended assignment. I hope my presentation has managed to reach your expectations, and most importantly, thank you so much for being such a great teacher for the past 2 semesters. I really enjoyed being your student, and inshallah, I hope to pursue my career in geophysics one day. Please pray for my success, and once again, thank you so much, Dr. Abdul Halim. Till we meet again, Assalamu alaikum warahmatullahi wabarakatuh.